Hello there, and welcome to the Sleepy Science Channel. Tonight, we're exploring one of the oldest and most beautiful ideas in all of science: the circle of life. It is the quiet pattern that connects forests, oceans, microbes, animals, and even the air you breathe. Nothing truly stands apart. Every living thing is part of a vast exchange that has unfolded for billions of years. The food we eat, the soil beneath our feet, and the breath in our lungs all carry stories from earlier lives. Leaves fall and forests rise again. Oceans bloom with life, then return their nutrients to the deep. Creatures are born, grow, transform, and pass their energy forward into the living world that follows. Seen from afar, life on Earth is not a straight line. It is a series of loops, cycles, and returning pathways that keep the planet alive. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, simply settle in and let your breathing slow. Allow your body to relax and your thoughts to drift. As the night grows deeper, we will wander through the remarkable cycles that connect every living thing. Let's begin. Every breath you take contains atoms once breathed by dinosaurs. The air around you is far older than any creature now alive. Earth does not keep making brand new atoms for each new generation. Instead, it reuses them again and again in an endless planetary exchange. A single breath may carry oxygen released by a forest this morning, nitrogen stirred up from the sea, and carbon dioxide exhaled by animals continents away. Over immense spans of time, those same atoms have passed through fern-filled swamps, volcanic skies, mammoth lungs, and the chests of creatures that vanished long before humans arrived. That means the boundary between past and present is thinner than it seems. When you inhale, you are not taking in something fresh from nowhere. You are borrowing ancient matter that has already belonged to countless living things. Breath becomes a kind of reunion, linking your sleeping body to vanished worlds through the simplest act of all. Your body is built from stars, soil, sunlight, and ancient seas. Nothing about you began with you. The calcium in your bones was forged in long dead stars that exploded before the sun was born. The iron in your blood came from the same cosmic violence. Yet those elements did not leap from space straight into human life. They spent ages moving through rock, rain, oceans, and the bodies of other organisms. Plants drew minerals from soil and powered themselves with sunlight. Animals ate those plants, or ate other animals, and passed that material onward. Seas once covered lands that are now dry. Tiny marine life helped shape the chemistry that later fed forests, insects, reptiles, birds, and mammals. In that sense, your body is a gathering place for worlds that should never have met. Starlight became chemistry. Chemistry became cells. Cells became tissue, memory, movement, and thought. You are not separate from nature's story. You are one of its most intricate rearrangements. Forests grow from the remains of creatures, leaves, and vanished worlds. A forest floor looks soft and simple from above, yet beneath it lies a layered archive of old life. Fallen leaves, splintered branches, dead insects, feathers, droppings, and hidden carcasses all sink into a slow process of breakdown. Fungi thread through the debris. Bacteria strip complex material into forms that roots can use. Worms and other small animals churn everything together until the ground becomes dark, rich, and astonishingly fertile. Even the deepest history is involved. Much of the carbon cycling through modern forests was stored long ago by earlier ecosystems, then shifted through air, rock, and water before returning to living tissue again. That means a towering tree is not only a product of sunlight and rain. It is also built from long vanished lives, recycled and rearranged into bark, sap, and leaf. When a forest rises, it rises from memory made physical. The living canopy depends on an enormous hidden inheritance below. The same carbon in your cells once drifted through alien airless space. Carbon is one of life's great shapeshifters. It forms the backbone of sugars, fats, proteins, and the molecules that help store and read genetic information. Yet before it became part of any cell, it had a much stranger history. Carbon atoms were forged in ancient stars and cast into space, where they drifted through cold clouds of dust and gas for unimaginable lengths of time. Some became trapped in the material that later formed the Sun, Earth, meteorites, and the early atmosphere. From there, carbon moved through volcanoes, oceans, rocks, and the first chemistry that edged toward life. It now passes endlessly between air, soil, water, and organisms. A carbon atom in your body may once have been dissolved in primeval seas, locked inside limestone, or floating through the dark between newborn worlds. That is what makes ordinary biology feel almost unbelievable. Your cells are not made from local ingredients alone. They are built from matter with a cosmic passport. Life survives by recycling almost everything, including bodies, breath, and waste. Nature is far less wasteful than human systems often are. In healthy ecosystems, what one organism discards becomes a resource for something else. Exhaled carbon dioxide feeds plants. Animal waste fertilizes soil and water. Shed feathers can line nests. Dead wood shelters insects, fungi, and mosses, while slowly releasing nutrients. Even bones and shells become valuable, providing minerals or habitats once they break down or are colonized. This constant reuse is not a side feature of life. It is the reason life can persist on a planet with finite material. Earth does receive energy from sunlight, but the matter itself is cycled through living and non-living systems over and over. That is why decomposers are as important as predators and pollinators. They keep the great exchange moving. Without recycling, nutrients would become trapped in useless forms, and ecosystems would slowly starve. A fallen tree can become a crowded city for new life. When a tree falls, it does not simply disappear from the story of the forest. It enters a new role. The bark begins to loosen and crack, creating shelter for beetles, spiders, and centipedes. Fungi spread through the wood and start digesting tissues the tree itself could not reuse in life. Mosses and lichens settle on the damp surface. Cavities hold water where insects breed and tiny creatures drink. As the log softens, salamanders hide beneath it. Small mammals nest nearby, and seedlings may sprout from the decaying trunk itself. These are sometimes called nurse logs, because they cradle the next generation of plants above the busy floor below. In some forests, young trees rise in straight lines because they all began on the same long, rotting giant. What looked like collapse becomes architecture. What seemed like loss becomes housing, food, moisture, shade, and nursery space. One body falls, and an entire neighborhood begins to thrive. The circle of life begins long before birth, in older lives. No new organism starts from nothing. Long before a baby animal draws its first breath, or a seed sends out its first root, the materials that will build it have already lived other stories. Nutrients in an egg or seed come from food gathered by a parent. That food came from plants, prey, fungi, or microscopic life, each shaped by earlier cycles of growth and decay. Even the body that carries new life was itself assembled from borrowed matter. In that way, birth is not the beginning of existence. It is the moment a much older stream of matter and energy takes on a new form. This changes how you see inheritance. It is not only genes that pass onward, but substance itself. A chick is partly built from grains, insects, and the minerals of the ground. A human infant grows from nutrients traced through farms, oceans, sunlight, and ancient geochemical cycles. New life arrives already carrying the world behind it. Every meal is a link in an ancient chain of survival. Eating can feel immediate and ordinary, yet every bite connects you to one of the oldest systems on Earth. Food is stored energy and borrowed matter passed from one life to another. A piece of fruit holds sunlight captured by leaves. Bread carries the work of wheat roots drawing minerals from soil and water from rain. Fish embody entire marine networks of plankton, currents, and smaller prey. Even a simple meal contains traces of landscapes, seasons, microbes, weather, and countless organisms that made it possible. Predators, grazers, pollinators, decomposers, and farmers all stand somewhere in that background. The chain can stretch astonishingly far. Grass feeds an antelope. The antelope feeds a lion. The lion's body later nourishes scavengers and soil. Nothing in that sequence exists alone. To eat is to join a transfer already underway, one that began long before people named it. Survival is never solitary. It is always built on relationships, exchanges, and inherited abundance. Nothing living stands alone. Every creature borrows life from others. Individual organisms can look self-contained, but life is deeply collaborative. Plants rely on sunlight, water, soil organisms, and often pollinators or seed dispersers. Animals depend on other species for food, shelter, cleaning, warning signals, and sometimes direct protection. Inside bodies, microbes help digest meals, make useful compounds, and shape immune defenses. Coral reefs are partnerships. Lichens are partnerships. Even many roots function through fungal alliances that expand their reach into the ground. Borrowing life does not always mean harmony. It can include predation, competition, and parasitism too. Yet even conflict reveals dependence. A hawk needs prey. A parasite needs a host. A forest predator may indirectly protect trees by controlling the animals that would overeat young shoots. This means survival is woven from connections rather than independence. No creature is a sealed unit moving through a separate world. Each one is supported, limited, nourished, and transformed by others in a vast living web that never fully stands still. A seed can sleep for centuries, then wake in rain. Some seeds live in a kind of suspended possibility. They are not dead, and they are not truly active either. Inside them, a future plant waits with extraordinary patience for the world to become favorable. A hard coat may shield the embryo from cold, dryness, microbes, and time itself. In deserts, this means waiting for rare rainfall. In cold regions, it can mean enduring winter until warmth returns. A few seeds have astonished scientists by sprouting after decades, and in rare cases far longer, once moisture, temperature, and light finally aligned. The delay is not laziness. It is strategy. By waiting, a plant avoids spending its one chance in the wrong season or the wrong year. That makes the seed one of nature's boldest inventions. It carries food, shelter, instructions, and timing in a package small enough to hide in dust, then rise when the moment is exactly right. Caterpillars dissolve inside cocoons before becoming something entirely new. Metamorphosis is far stranger than a costume change. Inside the chrysalis or cocoon, much of the caterpillar's body is broken down and reorganized. Tissues that once powered crawling and chewing are dismantled, while clusters of cells already present in the larva begin building wings, legs, eyes, and adult organs. The process is not simple destruction. It is controlled transformation, guided by genes and hormones that turn one kind of life into another with almost theatrical precision. The result can seem impossible because the two stages live so differently. One spends its days eating leaves. The other may sip nectar, fly long distances, court mates, and help pollinate flowers. It is the same individual, yet its world has been almost completely rewritten. Few images capture the circle of life so vividly. Growth here does not mean becoming a bigger version of what came before. It means becoming something that would have seemed unimaginable at the beginning. Some jellyfish can reverse their age and begin again. Among the strangest stories in biology is a tiny jellyfish with an ability that sounds like myth. Under stress or injury, instead of continuing toward death in the usual way, it can revert to an earlier life stage. Its mature body transforms back into a polyp, which is a simpler form attached to a surface. From there, it can grow again and produce new jellyfish. This does not make it magically indestructible. It can still be eaten, diseased, or destroyed. Yet the ability remains astonishing because it bends our ordinary sense of aging. Most animals move one way through life. They develop, mature, and decline. This creature can, in certain conditions, turn the arrow around. Scientists study it because it may reveal how cells change identity and how aging works at a deeper level. For everyone else, it offers something just as remarkable. It shows that life's pathways are wider and stranger than common experience ever suggests. Vultures keep ecosystems alive by thriving on death itself. Few animals have a worse reputation than vultures, and few deserve it less. They are among the most efficient sanitation workers on Earth. By locating carcasses quickly and consuming them before they rot extensively, vultures help prevent the spread of dangerous microbes that might otherwise linger in soil, water, or the bodies of less specialized scavengers. Their digestive systems are remarkably tough, capable of handling pathogens that would sicken many other animals. This makes them a protective force in landscapes where large creatures live and die regularly. When vulture numbers crash, the consequences can ripple outward. Carcasses remain longer. Other scavengers increase. Disease risks can rise for wildlife, livestock, and people. So the bird circling overhead is not just waiting for death. It is part of what keeps death from becoming a public hazard. In the circle of life, beauty does not only belong to feathers, flowers, and song. Sometimes it arrives bald-headed and brilliantly useful. Mushrooms turn fallen forests into food for future forests. When a forest drops branches, sheds trunks, or loses entire trees in storms, mushrooms often become the visible sign that transformation has begun. The true labor is done mostly by fungal networks threaded through wood and soil. These organisms release enzymes that can break down tough substances like lignin and cellulose, materials that many creatures cannot easily digest. By doing this, fungi unlock nutrients trapped inside dead timber and return them to circulation. Without them, forests would slowly bury themselves in undecaying debris, and essential elements would remain sealed away. Some fungi specialize in different stages of decay, so one wave of species may follow another as wood softens and changes. What looks like a simple mushroom after rain is only the fruiting body of a much larger hidden system. It is the visible bloom of a recycler at work. Forest renewal depends not only on green growth above, but on patient disassembly below. Wolves can reshape rivers simply by returning to a valley. When wolves were restored to Yellowstone, their influence reached far beyond the animals they hunted. Elk and deer did not vanish, but their behavior changed. They became more cautious in places where escape was harder, especially along some riverbanks and valleys. With less intense browsing in those areas, willows, aspens, and cottonwoods had a better chance to grow. As vegetation recovered, it helped stabilize soil and reduce erosion. Beavers benefited too, because they rely on woody plants for food and dam building. Their dams then slowed water, created ponds, and expanded wet habitat for many other species. In some places, channels became less eroded and more complex. The wolves did not touch the rivers directly, yet their presence rippled through prey, plants, and engineering animals until water itself behaved differently. It is one of the clearest examples of how predators can shape an ecosystem from the top down. A returning hunter can alter the land without ever moving a stone. Tiny plankton help produce much of the oxygen you breathe. When people think of oxygen, they often picture forests. Trees matter deeply, but a huge share of the world's oxygen production comes from the ocean. There, microscopic plankton, especially photosynthetic organisms such as phytoplankton, drift through sunlit waters and use sunlight to turn carbon dioxide and water into energy-rich compounds. Oxygen is released as part of that process. These tiny drifters are so small that many are invisible to the naked eye, yet together they form one of the great engines of the biosphere. They also sit near the base of marine food webs, supporting creatures that range from small zooplankton to whales. Their abundance can rise and fall with seasons, nutrients, and currents, creating blooms that can sometimes be seen from space. It is a wonderful reminder that the planet's life support systems are not always grand in scale. Some of the most important work on Earth is done by beings too small to notice. Flowers bribe insects with nectar to carry life onward. A flower cannot walk toward a mate, so it must persuade someone else to do the traveling. Nectar is one of its cleverest offers. Rich in sugar, it tempts bees, butterflies, moths, beetles, birds, and even bats to visit. While the visitor feeds, pollen sticks to its body and is carried to another bloom. What looks like a peaceful garden scene is really a busy exchange of fuel for transport. Many flowers shape this bargain with remarkable precision. Some hide nectar deep inside narrow tubes that only certain pollinators can reach. Others use color patterns visible in ultraviolet, which guide insects like landing lights on a runway. Scent matters too, and timing matters. Some blossoms open in daylight for bees, while others release fragrance at night for moths. Reproduction, then, is not left to chance. It is staged through appetite, movement, and reward, with sweetness serving as one of life's most successful invitations. Many plants need fire before their seeds can open. Fire can look like pure destruction, yet for some plants, it is the signal they have been waiting for. In certain ecosystems, especially dry forests and shrublands, seeds may remain sealed inside tough cones or fruits until intense heat arrives. Flames clear crowded vegetation, release nutrients into the ground, and open the canopy so sunlight can reach the soil. Then, after the blaze, the seeds are suddenly in a world with less competition and more space. Some species have evolved around this pattern so completely that reproduction works best only after burning. The fire does not interrupt their life cycle. It completes it. This changes the way you see a scorched landscape. Blackened earth may seem empty, but hidden within it are futures primed for release. When rain returns, seedlings can emerge in great numbers from a place that looked ruined days earlier. In some habitats, destruction is the doorway through which renewal enters. Some trees only release seeds after intense heat or smoke. Certain trees keep their seeds locked away with extraordinary discipline. Their cones may stay closed for years, even decades, while mature seeds wait inside. Only the heat of a serious wildfire, or in some species chemicals carried in smoke, triggers release. This adaptation is called serotiny, and it reveals how closely life can tune itself to disaster. In fire-shaped landscapes, ordinary years may be too crowded or shaded for seedlings to thrive. After a blaze, the ground is more open. Ash can enrich the soil, and the sudden flood of light gives young plants a better chance. By delaying release until that moment, the tree is not being cautious alone. It is choosing a battlefield after the smoke clears. This makes a cone something more than a container. It is a time capsule with a built-in alarm system, waiting for one of nature's fiercest events to announce that conditions are finally right. The moon helps time the breeding of many ocean creatures. The sea does not follow human schedules. It follows rhythms of light, gravity, tide, and season. And the moon is one of its great conductors. Many marine animals time reproduction to lunar cycles so eggs and sperm are released when currents, darkness, or predator patterns give them the best chance. Coral on some reefs can spawn in astonishing synchrony, with countless colonies releasing reproductive cells within a narrow window after a full moon. Certain worms, fish, and crustaceans also use lunar cues, whether directly through moonlight or indirectly through tides. The advantage is not only timing, it is coordination. When large numbers reproduce together, the sheer scale can increase the odds that fertilization succeeds and that some offspring escape being eaten. So the moon is not just a lantern above the ocean. It is part of an ancient biological clock. Whole communities beneath the surface are listening to its pull, then responding with astonishing precision. Horseshoe crabs still spawn by rhythms older than human history. Horseshoe crabs seem almost unreal, as if they wandered out of a much older Earth and never quite left. For hundreds of millions of years, their lineage has endured dramatic planetary change, and each breeding season they return to shore with a ritual that still follows the pull of tides and the phases of the moon. Females crawl onto beaches to lay clusters of eggs in the sand, while smaller males cling on or gather nearby to fertilize them. The scene feels ancient, because it is. Long before cities, writing, or our earliest myths, these animals were already timing reproduction to coastal rhythms. Their eggs then become vital food for migrating birds in some regions, tying a deep past to a living present. Even modern medicine depends on them, since their blue blood has long been used to test certain forms of contamination. They are not relics in the simple sense. They are old solutions that still shape life now. A mayfly may live for years, then fly for hours. Few creatures make the contrast between hidden life and visible life more dramatic than a mayfly. Most of its existence passes underwater as a nymph, where it feeds, grows, molts, and becomes part of streams and ponds for months or even years, depending on the species. Then comes a sudden transformation. It rises from the water, emerges into the air, and enters a brief adult stage, focused almost entirely on reproduction. Some adults live only a day, and some far less. Many do not even have functioning mouthparts, because eating is no longer the point. They dance, mate, lay eggs, and vanish. To us, that can seem heartbreakingly short. Yet the shortness is only an illusion created by what we notice. The long preparation happened out of sight. The airborne finale is the last bright moment of a much larger life. In that way, mayflies remind us that the visible chapter is not always the main one. Dragonflies begin life underwater before mastering the open air. A dragonfly seems built for speed and sunlight, but its first world is dark, wet, and full of ambush. The young form, called a nymph, lives underwater and is already a skilled predator. It stalks mosquito larvae, tadpoles, and small aquatic animals, using a remarkable extendable lower jaw to snatch prey with startling speed. There it may spend months or even years, depending on the species and climate, before climbing out of the water to transform. The outer skin splits, and the winged adult slowly emerges, pumps fluid into its wings, hardens, and takes to the air. The difference between the two stages is astonishing. One prowls like a hidden hunter among reeds and mud. The other becomes a glittering aerial expert, capable of sharp turns, hovering, and mid-air capture. yet both belong to the same life. It is one creature learning two different worlds, first below the surface, then above it with dazzling control. Frogs are born with gills, then trade water for land. The life of a frog begins in a form that seems to belong to another animal entirely. From jelly-like eggs in water-hatched tadpoles, small swimmers with tails and gills built for an aquatic world. They feed, grow, and breathe as creatures of ponds, streams, or quiet shallows. Then metamorphosis begins. Legs appear. The tail shrinks. Lungs develop. The digestive system changes, as diet often changes too. Little by little, the body that was suited for life in water becomes one that can leap, breathe air, and navigate land. It is a vivid replay of life's flexibility written into one individual journey. Frogs never become fully separate from water, of course. Their skin and reproduction still keep them closely tied to damp places. Yet the transition remains extraordinary because it turns one habitat into a nursery for a mother. A frog does not simply grow up. It crosses between worlds while still being itself. Eels begin life as transparent ribbons drifting across the sea. Freshwater eels feel mysterious even before you learn how they begin. Adults can live in rivers, lakes, and estuaries, yet many species start far out at sea. After spawning in remote ocean regions, their young hatch into flat, transparent larvae called leptocephali. These do not look like little eels at all. They resemble drifting glass leaves or ribbons, almost ghost-like in the water. Ocean currents carry them across great distances for months before they transform into the next stage, become more eel-shaped, and begin moving toward coasts and inland waters. There they may spend years feeding and growing before later returning to the ocean to reproduce. For a long time, people had no idea where eels came from, and their beginnings inspired all sorts of strange guesses. The truth turned out to be even more astonishing. A secretive fish of rivers and marshes begins with a long transoceanic childhood, almost invisible in the open sea. Emperor penguins survive winter by turning parenthood into endurance. In Antarctica, emperor penguins breed during one of the harshest seasons on Earth. After the female lays a single egg, the male balances it on his feet and covers it with a fold of skin to keep it from freezing against the ice. Then he remains there through the deep winter, while the female travels to feed at sea. During this time, he may go without food for many weeks, enduring darkness, brutal winds, and temperatures that can plunge far below freezing. Survival depends on cooperation. Males huddle together in dense groups, rotating positions so no one remains on the exposed outer edge for too long. When the female returns, often guided with astonishing precision, she may feed the chick from food stored in her body while the male finally leaves to eat. This is not merely reproduction. It is a test of timing, energy, and collective resilience. Parenthood here is not soft or easy. It is an act of extraordinary persistence. Octopus mothers may starve while guarding the next generation. For some octopus species, motherhood becomes a long vigil with almost no room for survival. After laying thousands of eggs, the female attaches them in sheltered clusters and begins to guard them with intense devotion. She cleans them constantly with her arms, removes debris, and fans them with water so they receive enough oxygen. During this period, she may stop hunting almost entirely. Her body slowly weakens, while her attention remains fixed on the growing young. In deep-sea species, this watch can last astonishingly long, stretching across months and, in rare cases, even years. By the time the eggs hatch, she is often near death or already dying. It is one of the starkest examples of life being spent directly on the future. She gives protection, movement, and time, then has little left for herself. The young drift away into a dangerous world, because one exhausted parent held the line until the very last moment. Some spiders let their babies eat them as first food. In a few spider species, the first meal a mother provides is her own body. The process sounds brutal to human ears, yet in evolutionary terms, it is a striking form of parental investment. After producing her brood, the female may feed the young with special nutritive fluid for a short time. Then, when they are large enough, they begin consuming her. Her tissues become concentrated nourishment delivered at exactly the moment their survival depends on rapid growth. In species where this happens, the mother has little chance of living long afterward anyway, so the body is converted into a final gift rather than left unused. The young gain an early advantage in a world where food can be scarce and danger constant. What seems shocking is also precise. The parent's life is transformed into momentum for the next generation. It is one of nature's clearest reminders that care is not always tender in appearance, though it is profound in purpose. Male seahorses carry pregnancy, then release living clouds of young. Seahorses overturn many expectations about how reproduction works. In these fish, the female deposits eggs into a special brood pouch on the male's body. He then fertilizes them and carries the developing embryos himself. Inside the pouch, the young receive protection, oxygen, and a carefully regulated chemical environment that helps them grow. In some ways it functions almost like a womb, though it evolved along a very different path. When the time comes, the male does not simply release a few babies. He goes through muscular contractions and pumps out dozens or even hundreds of tiny seahorses into the water. The scene can look like a living fountain erupting from an animal no larger than a hand. Yet the drama does not end in security. The newborns are on their own almost immediately, small enough to be swept by currents or eaten by predators. Even so, the sight of a father giving birth remains one of the sea's most remarkable reversals. Bees feed their sisters, their queen, and the future hive. A beehive is a place where feeding becomes a form of collective destiny. Worker bees, which are female, spend their lives gathering nectar and pollen, processing food, and distributing it through the colony. They feed growing larvae, sustain the queen, and support one another through constant exchange. Young workers may act as nurses before they ever leave the hive, tending brood with carefully prepared secretions and helping determine how the next generation develops. The queen herself depends on that labor, because her job is reproduction rather than foraging. Even drones, the males, exist within a system supported by workers. What makes this so fascinating is that the hive's future is literally fed into being mouthful by mouthful. Stored honey can carry the colony through difficult times, while pollen provides protein for developing bodies. In this society, nourishment is not private. It is shared, directed, and organized with astonishing precision, so that thousands of individuals can function as one thriving lineage. Ant colonies behave like one body made of many lives. An ant colony can seem less like a group of insects and more like a single creature spread across many bodies. No ant understands the whole system, yet together they solve problems of defense, construction, nursing, food collection, and waste management with startling efficiency. They do this through local rules, chemical signals, touch, and constant movement. One ant lays a pheromone trail to food. Others reinforce it. Workers respond to the needs nearest to them, and large patterns emerge without central command. The queen is important for reproduction, but she does not direct daily operations like a ruler issuing orders. Instead, the colony behaves like a distributed intelligence, adapting to damage, opportunity, and threat in real time. Some species build bridges from their own bodies or form living rafts during floods. When you watch them closely, individuality starts to blur. The true organism seems to be the colony itself, with each ant acting like a temporary cell in a larger living whole. Termite mounds breathe like giant lungs built from insects. A termite mound may look like a pile of hardened earth, but inside it lies sophisticated architecture shaped by countless small builders. In many species, the mound helps regulate airflow, temperature, and moisture for the colony below. Networks of tunnels and chambers guide the movement of gases so fresh air can enter and carbon dioxide can leave. Sunlight warming the outer surfaces, changes in wind, and differences in temperature all help drive this ventilation. The effect is so impressive that people have compared some mounds to breathing structures. They are not alive in the way lungs are, yet they perform a similar exchange for the colony. This matters because termites often live with delicate fungal gardens or dense populations that need stable conditions. A badly regulated home would become dangerous fast. So the mound is more than shelter. It is environmental engineering built grain by grain, turning soil into a shared machine that helps thousands or millions survive underground. Death does not end life's story, it feeds the next chapter. In nature, endings are rarely clean stops. They are transfers. When an organism dies, its body becomes a storehouse of opportunity for other living things. Scavengers arrive first in many landscapes, from vultures in open country to crabs along shorelines. Then come bacteria, fungi, insects, and other decomposers that dismantle what remains with astonishing efficiency. Proteins break apart. Nutrients seep into soil or water. Roots absorb what was once muscle and bone. New leaves unfold using matter that recently belonged to another creature. This is why ecosystems do not collapse under the weight of the dead. They are built to transform loss into continuity. A fallen bird may nourish beetles, microbes, grasses, and the predator that later eats the grazing animal fed by those grasses. The path is never sentimental, but it is profound. Life persists not by escaping death, but by making it useful. That is one of the deepest patterns on Earth. Baby sea turtles begin life by racing toward a lethal ocean. A hatchling sea turtle enters the world already surrounded by danger. After developing underground in a nest of warm sand, it breaks free with its siblings and scrambles toward the brightest horizon, which under natural conditions is usually the open sea. That frantic dash is one of the most perilous journeys in nature. Birds, crabs, fish, and larger predators all wait for the chance to strike. Heat can overwhelm them. Artificial lights can lure them inland. Waves can flip them back. Yet they keep moving because the ocean is both threat and destination. Once they reach it, the challenge only changes shape. For years, many drift through offshore currents in a phase researchers once knew little about. Very few survive to adulthood. Those that do may one day cross entire oceans and return, somehow, to nest near the same shores where they first emerged. Life begins with a sprint into risk, guided by instinct older than humanity. Salmon die after spawning and feed the forests they left. When salmon return from the ocean to the rivers where they were born, they bring far more than eggs and instinct. They carry marine nutrients into inland landscapes. After battling upstream currents, rapids, and predators, many Pacific salmon spawn and then die. At first, that can seem tragic or wasteful. In truth, it is one of nature's great transfers. Bears drag carcasses into the woods. Eagles tear at the remains. Insects, microbes, and scavengers finish what larger animals leave behind. Nitrogen and other nutrients from the sea enter riverbanks and forest soils where plants can absorb them. Studies have even found marine signatures in the wood of trees growing near salmon streams. That means part of the ocean can end up in the trunk of a forest giant, because fish made one final journey inland. Their last act nourishes young salmon, hungry animals, streamside plants, and entire ecosystems far beyond the water where the story seemed to end. Coral reefs are built by countless lives ending in stone. A coral reef can look like a colorful underwater garden, yet much of its grandeur comes from accumulation over immense spans of time. Reef-building corals are tiny animals that secrete hard skeletons of calcium carbonate beneath their soft bodies. As generations live and die, those mineral structures remain. New polyps grow on top of older layers. Bit by bit, a city rises. Fish shelter within it. Crabs, mollusks, worms, and algae find places to feed and breed. Over years, centuries, and far longer, the remains of small animals become vast architecture visible from space. This makes reefs both lively and deeply historical. A diver moving over living coral is also moving across the legacy of innumerable earlier organisms whose bodies helped form the foundation. Storms may break pieces apart, and waves may grind fragments into sand, but even that sand often began as reef. An entire ecosystem is built from the mineral afterlife of tiny creatures. Dead whales become deep-sea banquets that last for decades. When a whale dies and sinks into the deep ocean, its body can create one of the richest food events in that dark world. The fall to the seafloor may be hundreds or thousands of meters, and when it lands, scavengers quickly gather. Sharks, hagfish, and other mobile feeders strip away soft tissue in the early stage. After that, smaller organisms move in. Crustaceans, worms, and microbes continue the work, drawing energy from what remains. Even the bones become valuable because fats trapped inside them can support specialized communities for years. In the deep sea, where food is often scarce and arrives only in fragments from above, a whale fall is like a sudden city of abundance. Species may appear that are rarely seen elsewhere, each adapted to a different phase of the feast. One animal's end creates a long-lived oasis in darkness, proving that even the largest bodies can be transformed into opportunity far below the reach of sunlight. Bones on the seafloor can support entire hidden communities. Long after the flesh of a large marine carcass is gone, the bones can remain as islands of chemistry on the seafloor. They are not inert leftovers. They can leak compounds and hold rich stores of material that certain organisms are able to exploit. Microbes colonize them. Small invertebrates move in. Some species are so specialized that they seem to belong to this world alone. Among the strangest are bone-eating worms that bore into whale bones and rely on symbiotic bacteria to help unlock nutrients. The skeleton then becomes habitat, food source, and long-term anchor for a miniature ecosystem. This is especially important in the deep ocean, where hard surfaces are limited and energy can be hard to find. A set of bones offers both. What looks empty to us may be full of slow, hidden activity, with life assembled around the remains of something much larger. Even stripped down to mineral and marrow, a body can still host a world. Deep sea worms can live only on nutrients from decay. Far below the surface, where sunlight never reaches and food can be painfully scarce, some worms survive by specializing in one of the ocean's most unusual resources. They depend on decaying remains, especially the bones of dead whales and other large animals that sink to the seafloor. One extraordinary group, often called zombie worms, has no mouth and no stomach in the usual sense. Instead, the females send root-like structures into bone and house bacteria that help them draw nourishment from the rich material locked inside. Males can be tiny and live in close association with females, creating a life cycle that seems almost alien. These worms are not generalists roaming the seabed for scraps. They are tied to the chemistry of death in a very specific way. Their existence reveals how thoroughly life explores every opportunity. Even a skeleton in the dark can become a dependable food source if evolution finds the right partnership and the right body plan. Life around hydrothermal vents runs without sunlight at all. Most ecosystems on Earth depend ultimately on sunlight, but hydrothermal vents reveal another possibility. These openings in the seafloor release hot mineral-rich fluids from deep within the planet, often in total darkness. Around them, life flourishes by using chemistry instead of light as the base of the food web. Certain bacteria can harness energy from chemicals such as hydrogen sulfide, building organic matter through a process called chemosynthesis. Larger organisms then depend on those microbes directly or live in close partnership with them. Giant tube worms, clams, and other vent animals may carry symbiotic bacteria inside their bodies, turning chemical energy into living tissue in one of the strangest communities on Earth. The setting feels almost impossible, with crushing pressure, darkness, and water heated by Earth's interior. Yet life not only persists there, it thrives. These vents changed science by showing that sunlight is not the only path to a working ecosystem on our planet. Some bacteria eat rock, metal, or sulfur to stay alive. Not all life waits for sunlight, leaves, or prey. Some bacteria make a living from chemistry that seems almost impossible. They can draw energy by oxidizing sulfur, iron, manganese, or other inorganic substances found in rocks, sediments, and mineral-rich water. To us, stone feels lifeless, and metal feels industrial. But to these microbes, they can be part of a menu. In caves, deep underground and around mineral deposits, such organisms slowly reshape their surroundings as they feed. They can help form strange deposits, stain surfaces with vivid colors, and influence the chemistry of whole environments. Some even contribute to the weathering of rock, helping release elements that later enter wider ecological cycles. This matters because it expands the meaning of survival. Life is not limited to green landscapes or animal bodies. It can grip a dark mineral surface and begin building a living world from chemistry alone, one invisible reaction at a time. Microbes in your gut help digest food and train immunity. Inside your digestive system lives a crowded community that does far more than sit quietly in the background. Gut microbes help break down components of food that your own body would struggle to process alone, especially certain fibers and complex compounds from plants. In doing so, they produce useful substances that nourish cells lining the intestine and influence metabolism in ways scientists are still untangling. Their role does not end with digestion. From early life onward, these microbes also help teach the immune system how to respond appropriately. A body must learn when to attack and when to tolerate, and the bustling population in the gut is part of that education. When the balance of that community shifts, the effects can ripple outward. Appetite, inflammation, mood, and resilience may all change. So your sense of being one self-contained individual is a bit misleading. You are supported by a hidden crowd that helps keep the whole system working. You are outnumbered by microbes living on and inside you. The human body feels singular from the inside, yet it is also an ecosystem. Microbes cover the skin, line the mouth, inhabit the airways, and populate the digestive tract in staggering numbers. Estimates have shifted over time as measurements improved, but the central truth remains remarkable. Your body is home to an immense living population that shares your days whether you notice it or not. Different regions host different communities, each adapted to its local conditions. Oily skin supports one set of organisms. Drier patches support another. The gut hosts still more, shaped by diet, age, health, and environment. Most are not invaders. They are residents, and many are useful or harmless under ordinary conditions. This means the border of your body is less like a fortress wall and more like a busy coastline. Countless microscopic lives arrive, settle, compete, cooperate, and depart. To be human is also to be habitat, carrying a living crowd everywhere you go. Compost is not waste, but life reorganizing itself. A compost heap can look unimpressive from the outside, just a pile of scraps, peelings, stems, and old leaves. Inside, though, It is a scene of intense biological work. Bacteria, fungi, mites, worms, and many other small organisms move in and begin dismantling what was once food, plant tissue, or paper. Heat rises as microbes multiply and feed. Structures break down. Odors change. What seemed like leftovers starts becoming dark, crumbly material rich in compounds that plants can use. Nothing has vanished. It has been rearranged. The apple core is no longer an apple core. The fallen leaf is no longer a leaf. They have entered a busy transition where form is lost, so usefulness can return. Compost makes the circle of life visible at close range because it turns the embarrassing idea of waste into a lesson in continuity. It shows that endings often look messy while the next beginning is quietly being assembled. Soil is alive with billions of unseen partnerships and battles. Take a pinch of healthy soil and you may be holding one of the busiest places on Earth. It contains bacteria, fungi, archaea, protozoa, nematodes, tiny arthropods, and a tangle of roots exuding chemicals into the dark. Some organisms cooperate, trading nutrients or protection. Others hunt, infect, outcompete, or consume one another in a microscopic drama that never stops. Fungi may link with plant roots and extend their reach. Bacteria may cluster around those roots to feed on released sugars. Predatory microbes may attack neighboring cells. Small animals graze on the tiny life beneath them and release nutrients in new forms. This hidden activity helps determine whether plants thrive, whether carbon stays stored, and whether water moves cleanly through the ground. Soil is not just crushed rock mixed with dead material. It is an active living fabric full of negotiation and conflict. The ground beneath your feet is less a surface than a crowded biological frontier. Earthworms turn dead matter into rich ground for roots. Earthworms rarely get much admiration, yet they are among the quiet engineers of fertile land. As they move through soil and leaf litter, they pull dead plant material downward, chew it, and mix it with mineral particles in their gut. What emerges as castings is not simply dirt that passed through a worm. It is material altered in texture, chemistry, and usefulness. Their tunneling also opens channels that let air and water move more easily through the ground, which can help roots penetrate and grow. Over time, this constant stirring blends layers that might otherwise stay separate. In gardens, fields, and forests, worms help convert surface debris into a richer underground world where plants can draw what they need. They do not perform the whole miracle alone, but their contribution is extraordinary given how humble they seem. A soft-bodied creature with no limbs and no eyes can help build the conditions for entire landscapes of growth. Dung beetles build nurseries from waste that others avoid. What most animals leave behind as waste can become treasure in the right hands. Dung beetles find fresh droppings with astonishing speed, guided by scent and competition. Some roll portions away into neat balls. Others tunnel beneath the pile and drag material underground. This is not random scavenging. Often the dung becomes a nursery. Eggs are laid in or near these carefully prepared stores, so the larvae hatch surrounded by food. What seems revolting to us is, for them, a ready-made packet of nutrients, moisture, and microbial richness. Their work also benefits entire ecosystems. By burying dung, they help return nutrients to the soil, reduce fouling on the surface, and even limit places where certain parasites or pest insects might thrive. The result is both practical and elegant. Waste is removed, young are provisioned, and the ground is enriched at the same time. Few animals turn neglect into opportunity with such tidy efficiency. Carrion beetles bury small corpses to raise their young. Some beetles perform a task so startling it feels almost ceremonial. When they find the body of a small dead animal, such as a mouse or bird, A pair may begin digging beneath it until the corpse sinks into the soil. They trim fur or feathers, shape the remains, and prepare it as a protected food source for their offspring. In certain species, the parents stay to guard the brood and help feed the larvae, which is unusual care for insects. The burial matters because it hides the resource from competitors and slows the chaos of exposure above ground. What was a brief death on the surface becomes an underground nursery below. This is not scavenging in the casual sense. It is family planning built around precision, timing, and a very unusual inheritance. Their young begin life not on random scraps, but on a carefully secured body, prepared by attentive parents in the darkness of the soil. Scavengers can prevent disease by clearing death from landscapes. A dead body left in the open does not remain only a body for long. It becomes a growing chemical event, attracting microbes, insects, and animals, while warming air and moisture speed the spread of decay. Scavengers change that timetable. By locating carcasses quickly and consuming them, they remove nutrient-rich material before it lingers where pathogens and pest species may multiply more freely. This service is carried out by a wide range of creatures, from vultures and hyenas to crabs, foxes, and countless insects. Each works differently, but the effect can be similar. Death is processed faster, redistributed, and folded back into ecological cycles, with less chance of becoming a dangerous hotspot. In places where scavengers decline, carcasses can remain longer and the balance may shift in harmful ways. So the animals people often regard as unpleasant are often deeply protective. They help keep landscapes cleaner by refusing to look away from what others will not touch. Even ashes can feed grass, flowers, and future forests. After fire, the ground can appear stripped down to its bleakest form. Yet ash is not merely the sign of what was lost. It can also become part of what comes next. When plants burn, some of the minerals they stored are left behind in the residue, ready to be washed into soil by rain or worked downward by wind and small organisms. Depending on the fire and the ecosystem, this can create a short-term pulse of available nutrients that helps new growth gain momentum. Grasses may rise first. Flowers can follow. Seedlings may take hold in the open space where dense cover once stood. The exact outcome depends on weather, severity, and what survived below ground, but the principle remains powerful. Fire does not only erase, it transforms living tissue into another form but can still enter the cycle. The pale dust of a burned landscape may already be feeding roots that have not yet appeared. Some desert plants wait years for one perfect storm. In the desert, survival often depends less on speed than on patience. Some plants spend years as seeds, lying in dust that seems empty and lifeless, while they wait for the rare combination of rain, temperature, and timing that makes growth possible. A brief shower is not enough. Germinating too early could be fatal if the soil dries again at once. So these plants gamble carefully, with seeds that may remain dormant through one dry season after another until a truly promising storm arrives. Then, the response can be astonishingly fast. Seeds swell, roots push downward, stems rise, and flowers appear with a speed that feels almost impossible in such a harsh place. Whole landscapes can shift from bare ground to color in a matter of days. What looks like sudden abundance is actually delayed life, held in reserve through years of restraint. The desert teaches that timing can be as powerful an adaptation as strength or size. Bamboo can flower once, then die across whole landscapes. Bamboo carries one of the strangest reproductive schedules in the plant world. Many species grow for years, even decades, through spreading stems and underground rhizomes, then flower in a single great event before dying. Even more remarkable, large populations of the same species can bloom in synchrony across wide regions, despite growing in different climates and conditions. The timing seems to be built into the plants themselves, as if each clump is following an internal clock set long before. When the flowering finally comes, the landscape can change dramatically. Masses of seeds appear. Animals that feed on them may surge in number. Then the bamboo often withers, leaving behind open ground, and the next generation waiting to rise. It is a strategy that feels extravagant, almost theatrical. Years of quiet growth are followed by one overwhelming act of reproduction, then a collective disappearance. Few plants make the passage between persistence and surrender feel so immense in scale. Cicadas spend years underground for a few singing weeks. For most of their lives, cicadas are hidden beneath the ground, feeding slowly on fluids from plant roots in a darkness almost no one sees. Some species remain there for only a few years, while others in North America can stay underground for 13 or 17 years before emerging in enormous numbers. Then the surface world suddenly fills with them. They climb trees, split open their skins, unfold wings, and begin a brief adult life dominated by sound. The males sing with astonishing volume to attract mates, turning forests and suburbs into vibrating chambers of summer noise. After so many years of secrecy, the visible part is short. They mate, lay eggs, and die within weeks. The strategy is powerful because mass emergence can overwhelm predators. Birds and mammals may feast, but too many cicadas appear at once for all of them to be eaten. Time itself becomes defense. The underground wait is long, so the final chorus can be overwhelming. Some squid live fast, reproduce once, and vanish within months. Squid are often creatures of urgency. Many species grow quickly, hunt actively, and race through life on a schedule far shorter than most people would expect. Some reach maturity within months, reproduce once, and die soon afterward. That pace gives them an almost combustible quality, as if their lives burn bright and fast in the sea. They must feed efficiently, evade predators, and reach breeding condition in a narrow window. In return, they can turn food into movement and growth with astonishing speed. Their bodies are built for action, with jet propulsion, large eyes, and skin that can flash through changing patterns of color. Yet for all that brilliance, the future lies in eggs, not in long individual survival. The adults spend themselves and disappear. This kind of life history feels extreme, but it can work well in changing marine environments where rapid growth and swift reproduction offer an advantage. Some lives endure by lasting, others endure by racing. Annual plants bet everything on one brief season of growth. An annual plant lives with startling commitment. It germinates, grows, flowers, produces seeds, and dies all within a single growing season. There is no second spring for the same individual, no quiet return from underground next year. Everything must happen now. That urgency shapes the whole design. Resources go into rapid growth, fast reproduction, and the production of seeds capable of carrying the line forward after the parent is gone. In fields, disturbed soils, and places where conditions can change quickly, this strategy can be remarkably successful. An annual does not need to preserve a permanent body through cold, drought, or damage. It places its future in durable offspring instead. That gives these plants a very different relationship to time than long-lived trees or shrubs. They are opportunists, arriving quickly when conditions open, and departing just as quickly when the work is done. One season is enough, provided it ends with the next generation already waiting. Perennial roots survive winter while the visible plant disappears. A perennial can seem to die when winter arrives. Leaves blacken, stems collapse, flowers vanish, and the garden looks emptied of what was there before. Yet in many species, the true continuity lies below the surface. Roots, bulbs, tubers, rhizomes, or other underground structures remain alive through the cold months, storing energy gathered during the growing season and protecting the tissues needed for regrowth. The visible plant was only the seasonal expression of something more durable hidden in the soil. When warmth returns, those reserves power a fresh emergence. Shoots break upward, leaves unfurl, and what looked lost appears to come back from nowhere. This strategy allows a plant to retreat from conditions it cannot safely endure above ground, while keeping its place in the landscape. Winter becomes not an ending, but a withdrawal. The plant is still present, only concealed. In that sense, perennials teach a subtler version of survival, one based on endurance through disappearance. Autumn leaves fall so trees can survive the cold. Leaf fall can look like surrender, but for many trees, it is a carefully managed survival strategy. Broad leaves are excellent at capturing sunlight during warm months, yet they become risky when winter approaches. Cold air and frozen ground make it hard for roots to replace water lost from leaf surfaces. Ice, snow, and wind can also damage delicate tissues. So before winter deepens, deciduous trees begin withdrawing valuable nutrients from their leaves and storing them in stems, trunks, and roots. The leaves are then sealed off at their bases and dropped. Their colors often change first because green chlorophyll breaks down, revealing pigments that were already there or newly produced during the transition. What follows is not merely a pretty seasonal display. It is a tactical retreat from a dangerous season. By shedding vulnerable surfaces, the tree reduces water loss and avoids damage, standing bare through winter so it can return stronger when growth becomes possible again. Decay releases nutrients that would otherwise remain locked away. A dead leaf, a fallen branch, or the body of an animal still contains valuable elements, but without decay, those materials would remain trapped in forms that living organisms could not easily use. Decomposition breaks that lock. As microbes, fungi, and small animals feed, tear, digest, and transform organic matter, nutrients are released back into soil and water in forms that plants and other organisms can absorb. This is one of the great enabling processes of life on Earth. Without it, carbon, nitrogen, phosphorus, and many other essentials would pile up uselessly in the remains of the dead. Forests would starve beside heaps of untapped abundance. Lakes and fields would lose productivity over time. Decay prevents that kind of ecological paralysis. It is the mechanism that turns leftovers into availability. The process may look messy, but its outcome is elegant. Hidden within rot is a kind of liberation, where life gains access to resources that death alone had sealed away. Fungi and bacteria are the quiet engines of renewal. Much of Earth's renewal happens out of sight and without applause. Fungi spread through wood, leaf litter, and soil with thread-like networks that can reach astonishing scale. Bacteria crowd every damp crevice, every grain of compost, every surface where chemistry can be turned into metabolism. Together, they are among the most important recyclers on the planet. They dismantle complex organic matter, free nutrients, alter soils, shape the conditions for plant growth, and help keep ecosystems from choking on their own remains. The work rarely comes with spectacle. There is no roar, no migration, no obvious drama for most human eyes. Yet remove them, and the world would change beyond recognition. Dead material would accumulate. Nutrient cycles would stall. The continuity between one generation and the next would begin to fail. These organisms do not simply clean up. They prepare the stage for what follows. Renewal depends on a vast hidden workforce that turns endings into usable beginnings again and again. Life depends as much on decomposition as on birth. Birth is easy to celebrate because it is visible, dramatic, and full of promise. Decomposition is harder to admire, yet life depends on it just as deeply. New organisms need access to space, nutrients, and usable materials. Without decomposition, those essentials would remain tied up in dead tissue and abandoned structures. Forests would fill with undecayed trunks and leaves. Oceans would keep storing bodies without returning their elements to circulation. Soil fertility would fade. The young would be born into a world where the resources of the past were locked away beyond reach. Decomposition prevents that. It clears, transforms, and redistributes. It turns history into possibility. In this sense, every birth is supported by countless earlier acts of breakdown. The cradle and the compost heap belong to the same system. One creates form, the other frees substance. Together, they keep the living world from becoming either empty or clogged. Life continues because creation and unmaking are partners, not opposites. Forest fires can destroy life, then unlock astonishing rebirth. A wildfire can leave a landscape looking ruined beyond repair. Trees stand blackened. Shrubs vanish. The ground seems stripped to silence. Yet in many fire-shaped ecosystems, that is not the end of the story, but the opening of another phase. Fire clears dense growth, returns minerals to the surface, and exposes soil to light that had been blocked for years. Some seeds germinate better after heat. Some insects arrive only in burned wood. Grasses and wildflowers can surge into spaces that were once too shaded or crowded to support them. New habitats appear for animals that depend on fresh growth or standing dead trees. The exact path depends on the intensity of the blaze and the species present, but the pattern is powerful. A burn can reset competition and create room for new generations. What feels like total loss from one angle can, in the right setting, become a fierce and surprising invitation for life to begin again. After eruptions, bare lava can become living land again. Fresh lava looks like the opposite of a habitat. It is hard, dark, hot at first, and utterly without soil. Yet, given time, even that severe beginning can become living ground. Wind brings dust. Rain enters cracks. Minerals on the rock surface begin to weather under sun, water, and changing temperature. Then come the pioneers, often microbes and hardy organisms, able to cling where nothing softer yet exists. Tiny pockets trap more particles. Moisture lingers a little longer. Bit by bit, the surface changes from sterile stone into a place that can hold life. This transformation may take years, decades, or much longer depending on climate and the lava itself, but it happens. Volcanic islands and old lava fields around the world tell the same remarkable story. What once poured from Earth's interior as destruction becomes the foundation for roots, insects, birds, and entire communities. Even the newest rock on the planet can join the circle of life. Lichens help turn naked rock into future soil. Lichens are easy to overlook, yet they are among the first great settlers of raw stow. They are partnerships between fungi and photosynthetic partners, usually algae or cyanobacteria, and together they can live where many other organisms would fail. On exposed rock faces, lava flows, and wind-scoured surfaces, lichens slowly anchor themselves and begin a quiet transformation. They trap dust, hold moisture, and release compounds that help break down the mineral surface beneath them. This is not dramatic work. It is patient, almost invisible labor performed across years and centuries. But its effect is enormous. As rock weathers and organic material accumulates, tiny pockets form where mosses and other early colonizers can gain a foothold. In that sense, lichens are not merely surviving on bare ground. They are helping create the conditions that make later life possible. A future forest may owe its earliest chance to a crust of living partnerships spread across stone. Mosses often arrive before forests, beginning slow ecological succession. Before tall trees claim a landscape, The first green may belong to moss. These small plants can settle into thin soils, damp crevices, and newly disturbed ground where harsher conditions keep larger vegetation away. They do not need deep roots because they absorb water across much of their surface. That allows them to spread over rock, fallen logs, and raw earth, softening places that once seemed too exposed for life to gain momentum. Their presence changes the land in subtle but important ways. Moss can help retain moisture, reduce erosion, and gather particles that slowly build more hospitable ground. Small invertebrates move in. Seeds find better footing. Other plants begin to appear. Ecologists call this succession, the step-by-step replacement and enrichment of one community by another over time. Mosses are often early authors of that process. They write the opening lines of a much longer story, preparing the stage before shrubs, saplings, and eventually forests rise. A pond can age into a meadow over centuries. A pond may look timeless, but many are slowly changing from the moment they form. Sediment washes in. Leaves fall and settle. Aquatic plants grow, die, and add their remains to the bottom. Year after year, the basin becomes shallower. Reeds and rushes spread from the edges. Open water shrinks. Marsh plants take hold where fish once swam. Given enough time, what began as a pond can pass through wetland stages and eventually become a meadow or even woodland, depending on climate and drainage. This is not aging in the animal sense, but it is a kind of ecological life history. The body of water is gradually transformed by everything that enters it and grows within it. A dragonfly hunting over open water belongs to an earlier chapter than a butterfly moving through grasses in the same place centuries later. Landscapes, too, have biographies. A pond can begin as water and end as land through the patient work of accumulation. Coral islands can begin with tiny drifting larvae finding stone. Many coral islands owe their existence to beginnings so small they are almost unimaginable. Coral starts life as a drifting larva in the sea, tiny enough to be carried by currents across great distances. If it finds the right hard surface in warm, shallow water, it can settle, transform into a polyp, and begin building a mineral skeleton. One polyp alone changes little. But generation after generation, colonies expand, layer upon layer, until reef structures rise upward through time. Waves break coral into sand. That sand collects and shifts. Storms and currents pile it into bars and low islands. Seeds arrive. Birds visit. Plants take hold. What was once open water can become a place where crabs scuttle, palms root, and people someday stand. The astonishing part is the scale of the transformation compared with its beginning. A drifting speck meets stone, and over long spans of time, an island enters the map. Mangroves raise young fish while protecting coasts from storms. Mangrove forests stand where land and sea meet, rooted in mud that shifts with tides and salt. Their tangled roots create one of the most valuable nursery systems in the coastal world. Young fish, shrimp, and many other animals shelter there among the submerged branches, where predators often find it harder to chase them. Food is abundant too because falling leaves and trapped organic matter feed a rich web of small life. Yet mangroves do more than raise the next generation of marine animals. Their roots also bind sediment, slow waves, and help protect shorelines from erosion and storm damage. In that sense, they defend both the future of ecosystems and the edges of continents at once. A young fish hiding in mangrove shade is part of the same story as a village spared some force of a storm surge. These forests are nurseries, barriers, and engines of coastal life, all woven together in one extraordinary living structure. Kelp forests grow fast, die back, and feed the sea. Kelp forests can rise with astonishing speed in cold coastal waters, forming towering underwater stands from large brown algae anchored to the sea floor. They offer shelter for fish, sea stars, crabs, snails, and countless other organisms that use the fronds like branches in a submerged woodland. But these forests are not static. Storms can tear them loose. Seasonal changes can thin them. Grazers can reduce them. When kelp breaks free or dies back, the story does not end there. Drifting pieces become food for animals far from the forest itself, and fragments that sink can feed creatures on the sea floor. In this way, kelp exports energy across the marine world. A living forest supports one set of communities. Detached and decaying kelp supports another. The same organism provides architecture, shelter, and then nourishment after its structure is gone. It is a vivid reminder that in the sea, growth and breakdown often happen as parts of one flowing system. Seagrass meadows store carbon by burying ancient sunlight underwater. Seagrasses are flowering plants, not seaweed, and their meadows perform one of the ocean's quietest and most important tasks. Through photosynthesis, they capture energy from sunlight and turn carbon into living tissue. But unlike many systems where that carbon quickly cycles back out, seagrass beds can trap and bury organic material in the sediment beneath them. Their roots and rhizomes help stabilize the seabed, slowing water enough for particles to settle and remain. Over long periods, layer after layer of carbon-rich matter can accumulate below the meadow. In that sense, these underwater fields are storing sunlight from years long past in dark coastal mud. The result matters far beyond the plants themselves. Seagrass meadows provide habitat for fish, shelter for young animals, and grazing grounds for species like turtles and dugongs, while also helping lock away carbon that might otherwise return to the atmosphere. Some of the sea's most important climate work happens low and green beneath shallow water. Forest canopies, roots, and fungi trade water, sugar, and warning signals. A forest is not just a collection of separate trees standing near one another. It is also a network of exchanges moving above and below ground. In the canopy, leaves capture sunlight and turn it into sugars. Below, roots and fungal partners help gather water and nutrients from the soil. Those fungi can link multiple plants, forming pathways through which resources and chemical signals may move. Scientists are still working out the limits and meaning of these transfers, yet the picture is already fascinating. A shaded seedling may receive some support through fungal connections. Plants under attack from insects can alter their chemistry and sometimes trigger defensive changes in nearby plants as well. Water stress in one part of a system can influence another. None of this turns a forest into a thinking creature, but it does reveal a living community full of traffic, exchange, and response. The woods are less solitary than they first appear. Trees can feed their seedlings through underground fungal networks. A forest seedling growing in deep shade faces a hard beginning. It may have little sunlight, thin roots, and few reserves of its own. Yet below the surface, it can be connected to fungal threads that link roots across the forest floor. These fungi trade with trees, receiving sugars made in leaves and helping gather water and minerals from the soil. In some cases, carbon and other resources appear to move through these shared networks, which means a young tree may gain support from older neighbors during its most vulnerable stage. Scientists still debate exactly how often and how much this happens, but the idea itself is astonishing. The forest is not only a competition of trunks racing upward. It can also be a connected system where hidden relationships shape who survives the dark years below. A small seedling may stand in shadow, yet still be tied into a living underground economy older trees helped create. Some plants poison neighbors to gain more room for life. Not every plant competes through height, shade, or root spread alone. Some fight chemically. They release substances from leaves, roots, or decaying litter that can hinder the germination or growth of nearby plants. This strategy is called allelopathy, and it turns the ground around a plant into contested chemical territory. Black walnut trees are a famous example because they produce compounds that many other species struggle to tolerate. Certain shrubs, grasses, and invasive plants do similar things in their own habitats. The effect can be subtle or severe, depending on soil, moisture, and which species are involved. What makes this so fascinating is that a seemingly still landscape is full of invisible conflict. A plant does not need teeth or claws to shape its neighborhood. It can alter the chemistry of the soil and reduce the chances of rivals taking hold. In the circle of life, even rooted organisms can wage quiet wars for space and light. Orchids can depend on fungi before they ever see light. Orchid seeds are astonishingly small, almost like dust, and that tiny size comes with a cost. Unlike many seeds, they contain very little stored food for the embryo. That means an orchid cannot simply land, sprout, and power itself into early growth on its own reserves. Instead, it often depends on a fungal partner in the soil to provide crucial nutrients during its first stage of life. The fungus enters the young seedling's tissues, and the relationship helps the orchid begin development before it has leaves or enough photosynthesis to support itself. In some species, this dependence continues even later, and a few orchids rely heavily on fungi throughout life. So the flower people admire for elegance and rarity begins in near invisibility, helped by a hidden ally underground. Before it ever unfolds a bloom or reaches for light, its future may rest on a quiet partnership in the dark beneath the forest floor. Fig trees and fig wasps survive through an ancient partnership. A fig is not a simple fruit in the usual sense. It is more like a hidden chamber lined with tiny flowers on the inside. For those flowers to be pollinated, a very small wasp must enter through a narrow opening that seems barely possible to pass. In many fig species, each kind of tree is linked to its own particular wasp partner. The female wasp squeezes inside, often losing wings or antennae in the effort, and pollinates the internal flowers while laying eggs in some of them. Her offspring develop within the fig. Later, new wasps emerge, collect pollen, and leave in search of another fig at the right stage. The whole cycle is so tightly matched that tree and insect depend on one another for reproduction. This partnership has been shaped over immense spans of evolutionary time, producing one of nature's most intricate bargains. A whole forest can be linked to the fate of a creature tiny enough to miss. Cleaner fish survive by picking parasites from larger predators. On coral reefs, survival sometimes depends on turning danger into opportunity. Cleaner fish set up stations where larger animals come to have parasites, dead tissue, and loose scales removed from their bodies. The clients can include groupers, rays, and even predators that could swallow the cleaner in a moment under other circumstances. Yet during these interactions, aggression is often reduced. The cleaner moves over gills, mouths, and skin with remarkable confidence, while the larger animal holds still long enough to benefit from the service. This is one of the reef's most extraordinary truces. The small fish gains food from what it removes. The larger animal gains health and relief. There are risks, and there can be cheating on both sides, but the relationship is stable enough to shape daily life on many reefs. It shows that the circle of life is not built on conflict alone. Sometimes survival flourishes through moments of negotiated trust between unequals. Clownfish and anemones protect each other with borrowed defenses. A sea anemone's tentacles are armed with stinging cells powerful enough to deter many fish, which is why a clownfish weaving among them looks almost impossible. The fish is protected by a special mucus coating that helps prevent the stings from firing in the usual way. That allows it to live in a place most other animals avoid. In return, the anemone may gain several benefits. The fish can drive away some intruders, improve water movement among the tentacles, and leave behind nutrients in waste. The partnership gives the townfish a guarded home and gives the anemone a resident helper. What makes it so compelling is the way one species survives by using another species' defenses without being harmed by them. It is not armor the fish built for itself. It is protection borrowed through adaptation and familiarity. A living fortress becomes a household, and both partners are safer because they stay together. Oxpeckers ride giants, feeding on parasites and wounds. Across parts of Africa, large mammals may carry small birds on their backs as they move through grasslands and scrub. These are oxpeckers, and they spend much of their time clinging to animals such as buffalo, giraffes, rhinos, and antelope while searching for ticks and other material to eat. At first glance, it seems like an ideal cleaning partnership. The bird gets a steady meal. The mammal loses some parasites. Yet the relationship is more complicated than a simple favor. Oxpeckers may also feed at wounds and keep them open longer, which means the benefit to the host can be mixed. That complexity makes the partnership even more interesting because it shows how life rarely divides neatly into friend or enemy. The birds ride on muscle and hide like living passengers on moving continents, taking what they can from bodies far larger than their own. It is a reminder that even close biological relationships can be full of tension as well as advantage. Remoras travel with sharks, living from scraps and safe passage. A remora is built for attachment. On top of its head is a modified dorsal fin shaped into a suction disc, which lets it fasten itself to larger marine animals such as sharks, rays, turtles, and even whales. Once attached, it gains an extraordinary advantage. It can travel long distances without spending much energy, ride through a world of predators with some protection, and feed on scraps from its host's meals or on small organisms associated with the host's body. The shark does not usually gain much from this arrangement, though the cost is often small. What makes the remora so fascinating is how completely it is adapted to a life of borrowed movement. It is not merely following a giant. It is turning another creature into transport, cover, and dining opportunity at once. In the open ocean, where shelter is scarce and travel is costly, that strategy can make the difference between drifting alone and surviving in powerful company. Some birds spread forests by passing seeds through their bodies. A bird swallowing fruit may look like the end of a seed's chances, but for many plants, it is the beginning of a journey. Seeds that survive digestion can be carried far from the parent tree, then dropped with a packet of nutrient-rich waste that helps them start. This is one of the great ways forests spread across landscapes. Birds can cross rivers, clearings, cliffs, and damaged ground where seeds might never roll or blow on their own. Some species are especially important because they eat large fruits and move large seeds, which smaller animals cannot handle. Others scatter countless smaller seeds across wide territories every day. What matters is not only distance, but direction. A seed moved away from the parent may escape overcrowding, disease, or seed-eating predators concentrated nearby. So a bird in flight is also a courier of future shade. Forests do not only grow from the ground up, they are carried outward on wings. Fruit evolved sweetness partly to recruit animals as couriers. Sweetness is not only a pleasure for human taste. In evolutionary terms, it can be an advertisement. A ripe fruit is often signaling to animals that it is ready to be eaten, because eating is the very thing that helps the plant move its seeds. Sugars make the fruit attractive. Color changes make it easier to spot. Softer flesh makes it easier to consume. All of this can work together to persuade birds, mammals, and other animals to act as transport. The animal receives energy. The plant gains movement for its offspring. If the seeds survive the trip through the gut or are dropped elsewhere after feeding, the next generation gets a chance to grow away from the crowded shadow of the parent. This means a peach, berry, fig, or palm fruit is not simply food. It is part of a long negotiation between plant and animal appetite. The sweetness that delights the eater also serves the quiet ambitions of the seed within. Pollination turns hunger, scent, color, and timing into survival. Pollination is one of nature's most elegant acts of persuasion. A plant cannot go searching for a partner, so it must turn itself into an irresistible invitation. Color draws attention from a distance. Scent carries through air as a signal. Nectar rewards the visitor that arrives hungry. Timing decides who gets the message, with some flowers opening at dawn, some at dusk, and others only under very specific conditions. The result is not decoration for its own sake. It is survival built from attraction and precision. A bee, moth, bird, beetle, or bat follows its own needs, yet in doing so, it becomes part of a plant's future. Reproduction happens because appetite meets design at exactly the right moment. What looks like beauty in a field or garden is often strategy made visible. Every bloom is an offer, and every successful visit is a small victory in the long effort to keep life moving forward through another generation. Some flowers bloom for a single night to meet one pollinator. A flower that lasts only one night seems almost impossibly wasteful until you realize how exact its target can be. Some plants do not need a long season of visitors. They need one particular partner to arrive at one particular time. So they open briefly, release a powerful scent into the evening air, and present nectar or pollen just when the right pollinator is on the wing. Large white blossoms visited by night-flying moths are classic examples, because pale petals show well in low light, and fragrance travels farther in darkness than color can. In other cases, bats arrive after sunset to feed and carry pollen onward. The flower's short life is not fragility. It is precision. Energy is spent during the narrow window when success is most likely. Then, the bloom fades. The whole event can pass while most people sleep, a hidden performance of timing and partnership unfolding between dusk and dawn. Bats help create tequila, forests, and deserts full of fruit. Bats do far more than haunt old stores and dark skies. In many ecosystems, they are pollinators and seed dispersers on a grand scale. Nectar-feeding bats visit night-blooming flowers and carry pollen between them, helping plants reproduce across deserts and tropical landscapes. Some agaves depend heavily on bats, which means these flying mammals help sustain the plants connected to tequila production. Other bats eat fruit, then travel long distances before dropping or defecating the seeds, spreading the beginnings of future trees across clearings and damaged ground. In parts of the world where forests have been disturbed, bats can be among the first agents of recovery, carrying seeds into open areas where few larger animals may roam. Their work happens mostly after sunset, which makes it easy to miss. Yet whole plant communities depend on those hidden flights. A bat moving through the dark can be carrying tomorrow's flowers, fruit, and forest canopy with it. Hummingbirds fuel pollination by burning energy at astonishing speed. A hummingbird lives on the edge of energetic impossibility. Its wings beat so fast that it can hover in place, dart backward, rise vertically, and move from flower to flower with extraordinary precision. That kind of flight costs a tremendous amount of energy, which is why these birds must feed often on nectar-rich blossoms. As they do, pollen brushes onto their heads or bills and travels with them to the next flower. Plants adapted to hummingbird pollination often produce bright tubular blooms packed with sugar, offering fuel to a visitor that can burn through it with astonishing speed. The relationship is built on motion. The bird's appetite drives constant travel. The plant's structure guides where the bird feeds. This creates a lively exchange between flight and reproduction, where survival is measured in heartbeats and quick returns to the next bloom. A hummingbird is not only feeding itself, it is stitching plant futures together at dazzling speed. Elephants can create water holes that keep others alive. In dry landscapes, Water can mean the difference between survival and collapse, and elephants sometimes become the animals that help uncover it. Using strength, memory, and persistence, they can dig into riverbeds or dry ground where moisture still lingers below the surface. What begins as a search for their own relief can create access for many other creatures afterward. Smaller mammals, birds, and insects may drink from the hole once it is opened. In this way, the largest land animals can act as accidental providers in times of scarcity. Elephants also shape paths to water that other species follow, and their knowledge of seasonal movement can lead whole communities toward the places where life still has a chance. This makes them more than impressive herbivores wandering the landscape. They are ecosystem engineers with memories written into migration and behavior. When they find hidden water, entire neighborhoods of life may gather around what their bodies made possible. Beavers build wetlands that become nurseries for entire ecosystems. A beaver cutting branches beside a stream may seem like a simple woodland scene, but the consequences can spread across an entire valley. By building dams, beavers slow flowing water and create ponds and wetlands where there may once have been only a narrow channel. These new habitats transform the land. Sediment settles. Aquatic plants expand. Insects multiply. Fish, amphibians, waterfowl, and mammals find food, shelter, or breeding space in the changed environment. The wetland also stores water more effectively, which can reduce the harshness of drought and alter how the surrounding landscape responds to changing seasons. Young animals of many kinds benefit from these quieter, shallower waters, which is why beaver landscapes often become nurseries full of growth and motion. The beaver is working for its own shelter and safety, yet its engineering creates opportunity far beyond its lodge. A single family can turn a creek into a living workshop for many species. Sea otters protect kelp forests by eating hungry urchins. Kelp forests need more than sunlight and cold water. They also need protection from overgrazing, and sea otters are among the animals that can provide it. Sea urchins feed on kelp and can strip entire areas when their numbers grow unchecked. In places where otters are abundant, they prey on urchins and help keep that pressure under control. The result is larger, healthier stands of kelp that can support fish, invertebrates, and many other forms of marine life. Where otters disappear, urchin populations may explode, turning lush underwater forests into sparse barrens with far less shelter and productivity. This is a beautiful example of how one predator can support a habitat by choosing the right prey. The otter never touches the kelp as a gardener would. Yet by eating what would otherwise destroy it, the otter helps hold an entire underwater forest in place. Sometimes the protector of a landscape is also one of its hungriest residents. Sharks help balance oceans by removing the weak and sick. A shark is often imagined as pure threat, but in ecological terms it can also be a regulator of health and balance. By preying on vulnerable animals, including the weak, injured, old, or sick, sharks may help prevent some prey populations from becoming dominated by individuals less likely to survive and reproduce. Well, their presence also influences behavior. Fish, seals, and other marine animals may avoid certain places or feed more cautiously when sharks are near. That changes grazing patterns, movement, and pressure across the ecosystem. Remove large predators, and the effects can spread in surprising ways through food webs and habitats. This does not mean every shark is constantly improving the ocean like a careful manager, but it does mean their role is larger than fear suggests. They shape who feeds, who moves, and who survives. A shark's bite is only the visible edge of a deeper influence that can help keep marine systems from slipping out of balance. Predators can protect plant life without touching a single leaf. A predator does not need to eat plants to shape the fate of forests, grasslands, or riverbanks. Its influence can travel through the animals it hunts. When herbivores face a serious risk of being chased or killed, they often change where they feed, how long they stay, and how boldly they use exposed ground. That shift in behavior can spare young trees, tender shrubs, or streamside growth from being browsed too heavily. In some ecosystems, the mere presence of a predator helps create patches where plants regain ground because grazing animals no longer linger there so comfortably. This is one of the most fascinating indirect effects in nature. Teeth aimed at deer, antelope, or other herbivores can alter the future of leaves never bitten by the hunter itself. Life is linked by chains of consequence, not just direct contact. A stalking predator can shape the green world simply by making other animals nervous. Parasites shape evolution by forcing hosts into constant change. Parasites are among the most relentless drivers of biological change. They feed on hosts, exploit bodies, and spread through strategies that can be astonishingly refined. In response, hosts evolve defenses such as tougher barriers, smarter immune reactions, altered behavior, or new life cycle timing. Then parasites adapt again to overcome those defenses. The result is an evolutionary contest that never truly settles. This ongoing pressure can influence which genes spread through populations and which traits help individuals leave descendants. It may even help explain why so much life invests in genetic mixing, because variation can make it harder for parasites to exploit every host in the same way. What makes this so remarkable is that tiny organisms can help shape the destiny of much larger ones across immense stretches of time. A parasite is not just a burden on one animal or plant. It is a force that keeps pushing life to innovate, resist, and change in the struggle to stay one step ahead. Immunity itself is part of life's endless evolutionary arms race. An immune system is not a static shield that arrived finished and perfect. It is a living record of conflict shaped over immense time. Every virus, bacterium, fungus, and parasite that tries to exploit a body creates pressure for new defenses. In turn, those threats evolve ways to hide, invade, or mislead. The result is an arms race unfolding inside every generation. Cells learn to detect intruders, molecules mark danger, and memory helps the body respond faster the next time. Yet no victory is permanent. Pathogens change quickly, and hosts must keep adapting or fall behind. This is why immunity is both powerful and costly. It must be responsive without attacking too much, vigilant without becoming destructive to its own tissues. What feels like ordinary recovery from illness rests on an ancient struggle written into blood, lymph, skin, and cells. Every healthy body carries within it a battlefield shaped by countless past encounters. Sexual reproduction mixes old genes into never-before-seen combinations. Sexual reproduction does something astonishingly creative with ancient material. Instead of passing life onward as a near copy, it shuffles inherited genes into combinations that have never existed before. A child may carry familiar features, but the exact arrangement of traits is new. This mixing happens through the formation of eggs and sperm, where chromosomes are divided and exchanged in ways that generate variety before two parents' genes even meet. The result is not random chaos. It is structured novelty, built from old instructions, but arranged into fresh possibilities. In a changing world, that can be a profound advantage. New combinations may help some individuals resist disease, tolerate heat, digest different foods, or survive shifting conditions better than others. Sexual reproduction is costly and complex compared with simple cloning, yet life has returned to it again and again because variation is powerful. The future is not copied straight from the past. It is recombined from it. Mutation gives life new options when worlds begin to change. Mutation is often described as error, but without it, life would have far fewer ways to respond when circumstances shift. A mutation is a change in genetic material, and most do little or nothing useful. Some are harmful. Yet now and then one opens a door that did not exist before. It may alter pigment, shape a protein differently, shift development, or change how a body handles heat, cold, salt, altitude, or disease. In a stable world, such changes might remain rare and unimportant. But when climates move, habitats break apart, predators arrive, or food sources change, a once minor difference can become the key to survival. Evolution cannot plan ahead. It works with what variation happens to appear. Mutation supplies that variation, giving natural selection something to work on when older solutions stop fitting the world. In that sense, mutation is one of life's quiet sources of possibility, a generator of options for futures not yet arrived. Extinction clears space for entirely different forms of life. Extinction is loss on a grand scale, and nothing about it is gentle for the lineages that disappear. Yet in the long history of life, disappearance has often opened ecological space for very different survivors. When dominant groups vanish, habitats, food sources, and lifestyles that were once tightly occupied can become available again. Creatures that had lived in the margins may diversify into those openings, evolving new sizes, behaviors, and body plans over time. This does not make extinction good in any simple sense. It means only that evolution keeps moving through absence, as well as survival. The world after a loss is not the same world as before. Forests, oceans, and skies can be claimed by new rulers because old ones are gone. Some of the most dramatic turns in Earth's biological story begin with empty niches waiting to be filled. A vanished lineage leaves behind not only silence, but opportunity for something wholly different to emerge. The dinosaurs' fall helped mammals rise into new worlds. For much of the age of dinosaurs, mammals were present, but largely lived in the shadows of far larger and more dominant animals. Many were small, nocturnal, and limited in the roles they could occupy. Then came the catastrophe at the end of the Cretaceous, when a massive asteroid impact and its aftermath helped erase non-avian dinosaurs from most of the planet. The change was devastating, but it also transformed opportunity. With giant reptilian rulers gone, many ecological niches opened across land, water, and air. Mammals began diversifying into new forms with extraordinary speed over evolutionary time. Some became swift runners, some burrowers, some climbers, some swimmers, and eventually, some enormous. Predators changed. Plant eaters changed. Brains, senses, and body plans explored new directions. Humans are part of that distant consequence. Our own story depends on a disaster that ended another empire of life and left room for small survivors to expand into a very different world. Mass extinctions can reset the entire direction of evolution. Most extinction happens in an uneven, ongoing way, but a mass extinction is different. It is a crisis so sweeping that large portions of life vanish across many groups and habitats in geologically short spans of time. When that happens, evolution does not simply continue on the same path with fewer players. The direction itself can change. Entire dominant lineages may disappear. Food webs are broken apart. Landscapes and oceans are repopulated by survivors that suddenly face a transformed world. After such events, traits that were once marginal may become valuable, and groups that were once minor can expand dramatically. Earth's history includes several of these great resets, and each reshaped the possibilities that came after. The biological future on the other side was not pre-written. It emerged from survival, chance, and the opportunities left in the aftermath. A mass extinction is not merely an ending. It is a turning point where the whole trajectory of life can bend. Birds are living dinosaurs still carrying ancient survival stories. When a bird lifts from a branch or crosses the sky, you are seeing the last surviving lineage of dinosaurs in motion. This is not a poetic comparison. Birds evolved from small feathered theropod dinosaurs, and their bodies still carry that ancestry in bone structure, posture, eggs, nesting behavior, and the remarkable anatomy of feathers. The catastrophe that ended the non-avian dinosaurs did not erase the whole group. One branch survived and continued through time until it became the sparrows, owls, parrots, eagles, penguins, and hummingbirds of today. That means the dinosaur story never fully ended. It changed scale and took to the modern world in new forms. A robin on a lawn and a pigeon in a city both belong to an ancient lineage that endured one of Earth's greatest crises. Their songs, migrations, and courtship displays are part of a survival story stretching back to the Mesozoic. Dinosaurs did not only leave fossils, they still fly overhead. Human bodies still carry traces of life's oldest ancestors. The human body feels modern to us because it is familiar, yet it is assembled from features with very deep ancestry. Your spine reflects a vertebrate past. Your limbs follow a pattern inherited from long ago tetrapod ancestors. The jaw, middle ear bones, and arrangement of major organs all carry echoes of older chapters in animal evolution. Even early development reveals structures that make more sense when seen as inherited history rather than fresh design. We do not begin from scratch in each generation. We are built from modifications of ancient plans that worked well enough to be preserved and reshaped across immense time. This is why the body can seem like a museum that moves and speaks. New traits were added, old ones were repurposed, and some leftovers remain despite no longer serving their original role. To look at a human being is also to look at a long chain of survival written in tissue, bone, and shared biological architecture. Every embryo briefly echoes deeper chapters of evolutionary history. Early development is not a replay of evolution in any strict or simple sense. Yet embryos can still reveal striking traces of shared ancestry. As a vertebrate embryo grows, it passes through stages where certain features resemble patterns seen across other members of the group. These similarities reflect old developmental programs that evolution has modified rather than discarded. Structures appear, shift, merge, or disappear as the body takes shape. In human embryos, for example, there are early features that connect us to broader vertebrate heritage, even though they do not remain in the same form. What makes this so fascinating is that development preserves history in motion. The body is assembled using inherited instructions, layered and altered over vast time. Watching that process is like seeing deep ancestry flicker briefly through the making of something new. An embryo is not a museum exhibit, but during development it does reveal that the present body is built on very old biological foundations. Breast milk passes immunity from one life into another. Breast milk is not only food, it is also a transfer of protection. Along with fats, sugars, water, and proteins needed for growth, it carries antibodies and other immune factors that help guard an infant during a vulnerable stage of life. A newborn enters the world with defenses still developing, and this milk can help shield delicate tissues, especially along the gut and other surfaces where microbes first meet the body in large numbers. The transfer is intimate and practical at once. One immune system extends some of its knowledge and protection into another body that is only beginning to build its own long memory of the world. The composition of milk is dynamic too, changing over time to match the needs of the growing infant. What seems like a simple act of feeding is therefore also an act of biological tutoring and defense. Survival passes forward not only through genes, but through direct protective care after birth. The placenta is a temporary organ grown for one journey. Before birth, one of the most remarkable organs in nature exists only for a brief and vital purpose. The placenta forms during pregnancy as a living bridge between parent and developing baby. Through it, oxygen and nutrients pass inward, while waste moves away. It also produces hormones that help sustain pregnancy and regulate profound changes in the body carrying it. What makes it especially astonishing is that it is temporary. An organ this complex is built for a single journey, used intensely for months, then released once its work is done. It is not part of the body in the ordinary lasting sense, yet without it, mammalian life as we know it could not unfold. Within that brief span, it manages exchange, protection, signaling, and support with extraordinary precision. The circle of life includes structures that exist only to carry one new life safely from hidden dependence toward the threshold of the world. Menopause may help families survive by protecting grandmother's knowledge and care. Human life includes an unusual pattern among mammals. Women can live for decades after reproduction ends, and that long later life may have helped families and communities survive. One idea, often called the grandmother hypothesis, suggests that older women increase the success of younger generations through care, food knowledge, social support, and experience. In demanding environments, that help could matter enormously. A grandmother may know where resources can still be found in a lean season. She may help protect, teach, and provision children while mothers recover, travel, or care for infants. Her contribution is not measured in births alone, but in survival passed through memory and attention. This makes the end of fertility far more than a closing door. It may be part of a deeper human strategy, in which knowledge itself becomes a form of inheritance. In the circle of life, later years can nourish the future not through reproduction, but through presence, wisdom, and care. Grief itself may have evolutionary roots in social survival. Grief feels deeply personal, yet it may also reflect something ancient about how social life evolved. In species that depend on bonds, the loss of a parent, mate, offspring, or close companion can disrupt protection, learning, cooperation, and survival itself. Emotional pain may be one way evolution marks those bonds as vitally important. When connection matters, separation matters too. Elephants linger near bones. Some primates show distress after loss. Dolphins and certain birds have displayed behaviors that suggest social attachment does not vanish without consequence. In humans, grief can be overwhelming because our relationships are woven into identity, memory, and daily life. The ache may be part of the cost of being a species that survives through long dependence and rich social ties. This does not reduce grief to biology. If anything, it deepens it. Sorrow may exist because attachment mattered so much that evolution built pain around its breaking to reflect the true weight of the bond. Aging may exist because bodies invest more in offspring than repair. A body has limited energy, and evolution is often less concerned with indefinite maintenance than with successful reproduction. One influential idea in biology is that aging emerges partly because organisms invest resources in growth, survival long enough to reproduce, and the raising of young, rather than in perfect lifelong repair. Damage accumulates. Cellular systems remain impressive, but they are not flawless. Over time, wear, mutation, stress, and declining maintenance begin to show. From evolution's perspective, a body that survives well through its reproductive years, they already have done enough to pass on its genes, even if it later deteriorates. That can feel harsh, but it reveals something profound about life's priorities. Organisms are not built primarily for immortality. They are built to continue the lineage. Aging, then, may be one consequence of an ancient trade. The future is purchased by investment in offspring and by accepting that repair will never be endless, complete, or free. Some animals die after reproduction because survival has already been spent. In some species, reproduction is not followed by recovery, but by collapse. Pacific salmon are famous for this pattern, yet they are not alone. Certain insects, octopuses, and other animals pour so much energy into mating, migration, egg production, or parental effort that little remains for continued life. The body has, in a real sense, been spent. Hormones may shift. Feeding may stop. Tissues may deteriorate rapidly. From a human perspective, it can seem shocking that evolution would favor such a plan. If one huge effort produces more surviving offspring than repeated smaller ones, then the strategy can endure. Life does not always aim for longevity. Sometimes it aims for a single, overwhelming transfer into the next generation. That makes reproduction feel less like an event and more like a final expenditure. In these species, the future is purchased so completely that the parent's own survival becomes secondary or no longer necessary at all. Even stars take part by forging elements life must borrow. Life on Earth depends on materials that were not made here. In the early universe, there were mostly the lightest elements. The heavier ones needed for rocky planets and living chemistry were forged later inside stars and during stellar explosions. Carbon, oxygen, calcium, iron, phosphorus, and many other elements essential to bodies, cells, and bones were created in cosmic furnaces long before Earth existed. When stars died, they scattered those ingredients into space, enriching clouds of gas and dust that later formed new stars, planets, oceans, and eventually living things. That means every organism is participating in a cycle far larger than biology alone. The circle of life reaches backward into astrophysics. Your blood depends on ancient stellar events. Your teeth and skeleton carry the aftermath of long-dead suns. Life does not create its raw materials from nothing. It inherits them from the universe, borrowing matter forged in fire to build brief and astonishing forms. The carbon cycle moves through air, ocean, rock, soil, and flesh. Carbon is one of the great travelers of Earth. It moves through the atmosphere as carbon dioxide, enters plants through photosynthesis, passes into animals through food, returns through breathing and decay, and can sink into oceans, soils, shells, and stone. Some carbon cycles quickly through leaves, bodies, and air within days or years. Some becomes locked away in wood, deep sediments, limestone, or fossil fuels for ages beyond human memory. Volcanoes, weathering, currents, microbes, and fire all play roles in shifting it onward. What makes this so extraordinary is the range. The same element can drift in sky, dissolve in seawater, harden into rock, feed a forest, and briefly become part of a human thought. Carbon is a thread linking chemistry, geology, climate, and life into one moving system. The circle of life is not only about birth and death in organisms. It is also about the endless journey of matter through worlds living and non-living alike. The nitrogen in your body was once fixed by microbes. Nitrogen is essential for proteins, DNA, and many of life's most important molecules. Yet most organisms cannot use the vast reservoir of nitrogen gas in the atmosphere directly. Before it could become part of your muscles, skin, enzymes, or genes, it had to be transformed into usable forms such as ammonia or nitrate. That critical step, called nitrogen fixation, is carried out mainly by certain microbes. Some live freely in soil or water. Others form close partnerships with plants, especially legumes, helping feed roots while gaining shelter and nutrients in return. From there, nitrogen moves through food webs into animals and onward through waste and decay. This gives the element a remarkable story. Part of your body began in air that was chemically unreachable to you, until microscopic life made it available. The circle of life depends on these hidden chemists. Without them, much of the nitrogen around us would remain untouchable, and living bodies could never be built as they are. Life on Earth is a planetary loop powered by sunlight. Seen from far enough away, life on Earth can be understood as a vast planetary process driven mainly by incoming sunlight. Plants, algae, and photosynthetic microbes capture that energy and store it in chemical form. Animals eat plants or eat one another. Microbes decompose what dies. Nutrients cycle back through soil, water, and air. Energy flows through the system, while matter is endlessly rearranged. Sunlight powers growth, movement, repair, and reproduction, then escapes again as heat after doing its work. This means life is neither static nor isolated. It is a planetary loop in constant motion, linking atmosphere, oceans, continents, and the thin living skin wrapped around them. Every forest, reef, grassland, and body participates in that larger circulation. The circle of life is not merely a poetic image. It is a literal pattern of energy entering, matter cycling, and living forms rising and falling within that exchange. The planet stays alive because the loop keeps turning. The circle of life is really countless circles nested together. By the time you step back and look at the whole picture, there is no single circle of life. There are circles within circles, each operating at its own scale and speed. Cells recycle molecules. Bodies pass energy through food webs. Forests regrow from decay. Oceans circulate nutrients across vast distances. Species evolve, flourish, and disappear. Elements move between stars, planets, rock, air, water, and flesh. Some cycles last seconds. Some last seasons. Some stretch across millions of years. All of them overlap, influence one another, and create the living world we know. That is what makes the idea so beautiful. The circle of life is not one tidy ring that begins and ends in a simple place. It is a nesting of patterns, each feeding the next, from the smallest microbe to the largest planetary system. To live is to enter those loops for a while, borrow from them, add to them, and then pass onward into the next turning. As we come to the end of our journey through the circle of life, we have wandered through a world where nothing truly stands alone. We have followed ancient atoms through breath and bone. We have watched seeds sleep through long silence, then wake. We have seen forests rise from decay, reefs built from countless tiny lives, and oceans sustained by creatures too small to see. We have followed salmon inland, turtles toward the surf, fungi through fallen wood, and starlight itself into the living substance of Earth. And perhaps the most beautiful part of all is this: life is never only about beginnings, and never only about endings. It is about passing onward. A leaf becomes soil. Soil becomes root. Root becomes flower, fruit, feather, fur, flesh, and breath. Rivers carry it. Wind scatters it. Fire changes it. Time folds it back into the waiting world again. So now, let that thought grow softer in your mind. You do not need to hold every detail. You can let the images drift. Dark forests breathing after rain. Coral cities beneath slow water. Moonlit beaches. Quiet ponds changing by degrees. Great living networks below your feet and above your head. Always moving. Always returning. Thank you for spending this time here with me on the Sleepy Science channel. If you enjoyed this sleepy journey, I would love for you to like, subscribe, or leave a comment below. And if you are somehow still awake, there will be another video waiting for you on screen in just a moment. But for now, let your thoughts loosen. Let your breathing slow. Let the day fade gently into the distance as the living world keeps turning without hurry around you. Sleep well, and good night.